Okay, I record.
So, shall we start? So I'm very glad to introduce today George MAILATH from the University of Pennsylvania and from the Australian National University, who is one of the major figures these days in economic theory and game theory. George is a fellow of the American Academy of Arts and Sciences and a fellow of the Econometric Society and a bunch of other societies, the Game Theory Society. His research is game theory, pricing, repeated games, social choice, name it. George had impact on this area. He authored 2 books. The first one with Larry Samuelson on repeated games and reputation, and then a recent one on modeling strategic behavior. So we are very happy to have George today. And George, Zoom is yours.
Thank you. Thank you. Those very kind words. And thank you for coming this morning to hear the talk. So what I'd like to talk about, and let me just first say, I don't have any co-authors on this call. So if anybody has any questions, please just speak up loudly, and it's much more fun to give talks when there's interactions rather than just talking to a TV camera. So please, I encourage you to ask questions and make comments. So what I'm going to talk about today is joint work with Hal Cole, Dirk Kruger, 2 of my macro colleagues from Penn, and Yena Park, who was a macro student many years ago, University of Rochester, and just moving to Korea. So what we're talking about today is self-enforcing agreements, and we're used to thinking about equilibria of repeated games being a model of institutions as describing self-enforcing agreements. And so that basically means that we're thinking about a scenario where agents have a shared belief in future behavior, and in particular, a shared belief in future cooperation. But it's also a familiar idea that this belief in the possibility of future cooperation is a two-edged sword. The same way it can support behavior and deter opportunistic behavior, it could also encourage group deviations, coalitional deviations. And coalitional deviations can undermine the original equilibrium. Our interest here is to understand the impact of the fact that these beliefs are often tenuous. When we look out there in the real world, particularly today, we see some instances where this belief seems to be solid and institutions are working well. And yet, unfortunately, we've been surprised recently how fragile some of these institutions are, how this shared belief in future cooperation can be undone. And so that's what, broadly speaking, we're interested in understanding. And we're going to look at a particular example where future cooperation is important, and that's insurance. In particular, self-insurance, where a group of agents subject to idiosyncratic income shocks can share income and smooth out these shocks. Now, before I go into a bit more, let me just quickly make a few comments about the related literature to sort of try to put this into context. The idea that coalitional deviations and more generally renegotiation proofness is something we should worry about is, of course, an old idea. I've put up a few of the classic references on there, and they all share the basic idea that a putative agreement is destabilized if at some point there is a dominating agreement available to some or all of the players. Now, a critical feature of all of this work, though, is that when there is such a dominating agreement available, it's assumed that it will be implemented, that there isn't any friction in imposing this dominating agreement. And what we're interested in doing is trying to understand the fact that these agreements can be, even if they're available, may not be possible to be achieved, and this can have an impact on the original agreements that might be reached. There's also a literature on risk sharing with limited contract enforcement, which is related to what we're doing here, and endogenous outside options and risk sharing with coalitional deviations. The Jennecott and Ray paper is particularly relevant, and I'll say a few more words about that paper in a few minutes. Now, at a very high level, what we're interested in doing is, as I said, understanding what the impact is of being hard or easy to reach an agreement. And it's useful to have a simple phrase to capture that. And for want of a better word, and because economists like giving names to things, we're going to call this ability to reach an agreement. So, yes. Was there a question? No, okay. So we're going to call this ability to reach an agreement social capital. And the idea is that if we have high social capital in a group, then this group finds it easier to reach an agreement. If the group has low social capital, then they find it difficult to reach an agreement. So broadly speaking, what do we find? Well, if we have a group with very low social capital, so it's very difficult for them to reach an agreement, then if they are able to reach an agreement, they don't have to worry about coalitional deviations because they know that there's low social capital, and so there isn't any significant threat. And so we have a pretty standard situation. As the social capital in the community increases, now coalitional deviations are going to become a binding concern. And as soon as coalitional deviations do become a binding concern, we can no longer achieve the first best insurance, the efficient outcome in which we're sharing all income equally. And when this equilibrium insurance is imperfect, this is also going to mean that it's going to be non-stationary. And what we're going to see is that if an agent is poor, they are receiving some insurance, but they're going to receive more insurance in the agreement if they were more recently rich. Or in other words, you're much better off being recently poor than being long-term poor. And then finally, if there is a lot of social capital, if it's easy to reach agreements, then it's possible that the threat of coalitional deviations imply that we no longer get any increase in the value of equilibrium insurance, and the equilibrium actually has to involve some utility burning. And I'll explain what I mean by utility burning when we get to that point in the talk. Okay, so that's at a very broad brushstroke introduction, and I wouldn't be surprised if you're a little puzzled as to what's going to be happening. So unless there are any questions, I will now describe the model. Okay, excellent. So I'm going to use a standard benchmark model that economists use to understand insurance. So we're going to think about a world of a continuum population of ex-ante identical risk-averse agents subject to income risk. Each individual in each period with probability 1/2 has low income. With probability, they have high income. So each individual is subject to idiosyncratic income shocks. There's no storage, so individuals can't save against, if they're rich today, they can't save some for consumption tomorrow. I'm going to denote the possible income realizations as L and H, and they're set by capital H, and Y bar will be average income. The advantage of looking at a large population is that this means that when I look at any large coalition, so a positive measure set of agents, there will be no aggregate risk. So all of our focus will be on how we allocate risk among the agents, not how do we deal with aggregate risk. And this is an important difference from what we're doing with what the paper I mentioned earlier called Jennecott and Ray. Jennecott and Ray are looking at a very similar problem, but they have a finite set of agents. So when they're looking at a coalitional deviation, this means that a smaller set of agents are going to leave the current arrangement and try to self-insure. But because it's a smaller finite set, they have less ability to self-insure. They're going to be subject to more aggregate risk. And so Jennecott and Ray can talk about questions like what is the optimal size of the coalition. In contrast, we are going to be looking at large coalitions because we don't want to be distracted by questions of size of optimal size of coalitions. And we want to be looking at a recursive problem. I'm going to denote the individual's utility function by little u, which is going to be strictly concave, and our agents will maximize the average expected discounted sum of utility. I'm going to denote the discount factor by beta, and this is how you can tell this is a macro paper. I tried to convince my colleagues to use delta. I got to average utility. So that I viewed as a major success. So I went with that, and we are stuck with beta. In the absence of insurance, each agent's flow utility is going to be what? Well, ex ante with probability 1/2, the agent has low income. With probability 1/2, the agent has high income. So their average utility is, I'm going to denote by VA, and I'm going to call that the autarkic utility. So this is the utility that the agent has in the absence of insurance. Since we're measuring long-run utility as the average expected discounted sum, VA is also the value of to the agent in the long run. So now I need to tell you how we're thinking about coalition formation and deviations. We're going to start in period 0 with the planning and contract. This is when the grand coalition gets together and tries to reach an agreement. We're going to measure the ability of our coalition to reach an agreement in a very crude way. I've got this probability pi, which we'll call the social capital. And pi tells us the probability with which an agreement is reached. And in this paper, we're going to treat pi as exogenous. We should, of course, be also modeling pi and trying to understand the ability of agents to reach an agreement, but we can only do so much in one paper. If no agreement is reached, then I'm just going to assume that they're stuck in autarky forever. If they do reach an agreement, what have they agreed to? They've agreed to a plan for sharing of income in every future period. So it's a social norm over time paths of consumption. Now, what does risk sharing mean? This means that in every period, agents who have high income in that period are sacrificing some current consumption so that the currently poor agents can have a higher consumption. And in exchange, they're being promised future insurance. But the agents who are currently rich always have the opportunity of saying, you know what, we're currently rich, we're Catalonia, we're the UK. What we should do is just leave the current arrangement, eat our current income, and then because we're a large coalition deviating, we can still self-insure tomorrow. So this is a threat that could that these guys could do. Of course, if they're going to attempt to form a new coalition, they have to reach an agreement. And I'm going to use the same probability pi because the social capital that describes the social cohesiveness of the large community also applies to these large coalitions, these subsets of agents. And the attempt to form this new coalition succeeds with probability pi, but fails with probability 1 minus pi. The critical assumption we're making in this sequencing is that the agents need to succeed first before they try to form the new agreement. So any attempt to succeed brings with it the risk that with probability 1 minus pi, they'll be an autarky and they'll only succeed with probability pi. And so any agreement that these agents are going to reach, whether it's in period 0 or in any succeeding coalition, is going to be made understanding that there's always the possibility in the future some subset of agents will again succeed. And so any agreement the agents come to today has to be robust to this threat. All right, so let me just stop for a second and ask if there are any questions to this broad brushstroke. Okay, excellent. So now let me just pin down some notation so I can define formally what our equilibrium notion is. So what are the agents going to be bargaining over? What are they going to try and reach an agreement on? They're going to reach an agreement on a consumption allocation. What the consumption allocation has to do is to specify for every agent, for every sequence of income shocks that that agent could have received, what will their current consumption be? Because I'm looking at a world with a continuum of agents, I can look at a consumption allocation that is anonymous, that any two agents who have received the same sequence of income shocks will receive the same consumption. So the consumption allocation C here is a complete description of what's going to be happening in our society. The ex-ante utility, so in that initial period when all the agents, before there have been any realization of income shocks, we've got a continuum of identical agents. Each of their agents' utility from an arbitrary consumption allocation is going to be what? Well, there's my normalization factor 1 minus beta. We're summing over every period tau. We're taking expected values over all possible income histories of income shocks up to period tau. This is the probability that income sequence is realized. C of y tau, and I'm using superscripts to denote histories, subscripts to denote periods. So y super t is the history of income shocks. Y sub tau would be the income shock in period tau. C of y tau is the consumption allocation in period tau to an agent who has received a sequence of income shocks, y1 through y tau, and then this is his flow utility u, and so this is the expected discounted average utility. After any history, there could be a deviation. Without loss of generality, and in the talk I'll just focus on deviations by agents who have received the same sequence of income shocks. Since I've only got 2 possible income realizations in each period, there's a continuum of agents. There will always be a positive measure set of agents who have received the same sequence of income shocks. And so I can just look at the continuation utility that every agent who received the same sequence of income shocks, yt, what is their continuation utility? And so it looks a lot like the ex-ante utility, except that in that first period, in period t, we know what their consumption is. It's deterministic under the allocation. It's just the utility of consumption at that income sequence. We also need to worry about what the agent can get if they succeed. Well, if they succeed, they're going to have some new consumption and successfully reach an agreement C. They're going to have a new agreement. And so what are they going to get from that? Well, in the first period, since I'm restricting attention to deviations by homogeneous coalitions, all agents have the same income, so they're just going to consume their current income. And so there's their current utility. And then the flow, what do they get in the future? Well, with probability pi, they successfully agree on C, and so there's the ex-ante utility from that agreement. And with probability 1 minus pi, we're an autarky. And we have to discount by beta. So with that under our belts, we can now describe the equilibrium. An allocation is going to be an equilibrium if it does what? Well, when the agents are trying to reach an agreement, they want to reach the best possible agreement. Since they're doing this in period 0, they want to maximize the ex-ante utility. All of the agents are the same. But there are some constraints. The first one is just resource feasibility. We can't consume more in a period than the resources we have available. So because of the assumption on the continuum, the probability of an income sequence yt is also the fraction of the population that has received that income history. So this is the fraction of the population with that income history. This is the total consumption of that income history agents. And so this is the total consumption under C in period T, and that should be equal to the average income available. Now I need to describe how we're capturing the threat of coalitional deviations. And we're going to do this in a very weak way. So let's suppose our agents successfully reached an agreement, thinking that this agreement C will hold in all future periods. This means they think C is incentive feasible. Now let's, for the sake of argument, suppose that after some sequence of income shocks, Y super T, this sequence of income shocks has the property that the agents who receive that sequence of income shocks get strictly higher utility from succeeding, consuming their current income, and with probability pi, agreeing to the original agreement. After all, the original agreement people thought was a good agreement. So if it was good enough for the original coalition, it should be good enough for the coalition. If this total utility here is strictly greater than the continuation utility being in the agreement, this coalition is going to deviate. But then this means that the original agreement was not a good agreement because it contained the seeds of its own destruction. And so this is what we're going to mean by an equilibrium. Any questions? Excellent. Okay, so just to fix ideas, let's first of all think about when complete insurance could be an equilibrium. And what do I mean by complete insurance? Complete insurance is where in every period, we just pool all of the realized income, which is average income Y bar, and share it to all the agents. So each agent's consumption is the utility of Y bar. And this is the best possible ex-ante utility. For complete insurance to be in equilibrium, we're going to need that this, and so notice here that under this complete insurance, this is a history independent insurance scheme. All agents, no matter what their histories are, receive the same consumption in every future period. So in order for complete insurance to be in equilibrium, we're going to need that the rich agents, like people who in this period have high income, are better off sticking with the agreement and getting first best utility rather than consuming their high income today, 1 minus beta times utility of high income, and tomorrow having seceded with probability pi getting first best insurance and with probability 1 minus pi autarky. Let's suppose that we had high social capital, that pi was equal to 1. Well, if pi is equal to 1, this inequality has to be violated because when pi is equal to 1, the rich agents know that they could just not sacrifice any current income. No, they don't sacrifice any current consumption. And then tomorrow they just self-insure and get first best insurance. So that's a problem. So in order for first best to be in insurance, we need pi not to be too large. And I'm going to denote that critical value of social capital by first best. And so this first best level of social capital is a level of social capital at which the high income agent's incentive feasibility constraint is just binding, while the low income agent's incentive feasibility constraint is slack. And if agents, of course, are too impatient, no matter how low the degree of social capital is, we're not going to get an equilibrium. Our interest, though, is not in first best insurance, but just characterizing in general what are the possible levels of equilibrium insurance as we think about varying social capital. So there's the definition again. So first, a couple of preliminary comments. This problem is always well defined because autarky is always internally incentive feasible. The consumption allocation in which we don't do any risk insurance trivially satisfies this inequality constraint because I've just got current income in each of these arguments. Moreover, because the constraints are weak, the set of resource and incentive feasible consumption allocations is closed. We've got a continuous objective function, so that's not a problem. Equilibrium always exists. Characterizing what this equilibrium looks like, though, is much harder. The big problem is that this internal feasibility constraint generates a non-convex constraint set because we've got a concave function here on the wrong side of the inequality. Putting it differently, think about changing the consumption allocation as we're trying to maximize the objective function. We're also making the constraints tighter, and we're making them tighter in a awkward way. So the way we get a handle on this is to follow an indirect route. We're going to be looking at fixed points. So in order to motivate this, I'm going to now look at a version of the equilibrium optimization problem where I get rid of the irritating concave function as a function of C on the right-hand side of the inequality. So I'm going to call that exogenous incentive feasibility or F incentive feasibility. So I've just replaced the irritating green term here with my capital F. So now, since I'm treating F as exogenous, as I vary F, there is the possibility that the constraint set becomes empty. If we have an equilibrium allocation C dagger, then we know, because it's incentive feasible, it satisfies this inequality, which I'm indicating now. And so this trivially means that C dagger is going to be exogenously incentive feasible for a particular value of F dagger, which is just the convex combination of the ex ante value of C dagger and autarkic utility. But more generally, I'm thinking about F just as being exogenous. So, motivated by that, think about the following mapping T. So what does T do? T is a mapping that takes as the input an exogenous value of the outside option in the continuation value, capital F, and then calculates, well, V star of F is the value of this problem here. So it's the ex ante value of the optimal allocation where we have to satisfy the exogenous incentive feasibility constraint. And then we include the friction of the perhaps not reaching an agreement. That gives me T. So let's suppose I found a value of this exogenous outside option F, which is a fixed point of this mapping T. And let's suppose that C dagger is the consumption allocation that achieves V star of F. Then it turns out that F is the only fixed point. That's pretty straightforward once you see that the constraint set here is becoming tighter as we increase F, while, which means that V star of F is going to be decreasing. And C dagger is going to be unique equilibrium allocation. And F is going to be the ex ante value of this equilibrium. So why, I'm sure many of you have already seen where this is going. This fixed point property, if we do have an allocation C dagger whose value achieves this fixed point, I have actually found a stronger notion of equilibrium. I was deliberately calling the earlier incentive constraint internal incentive feasibility because I was constraining the kind of agreements the deviating coalitions could achieve. If I found a fixed point F in this problem, I've in fact found a consumption allocation that is robust in a much stronger sense. It's externally incentive feasible. It is robust to the threat that a coalition could deviate no matter what kind of agreement the coalition itself would like to achieve, subject only to the constraint that the deviating coalition is also worried about further deviations. So if we have an allocation that satisfies this stronger notion of coalition proofness, and this external incentive feasibility is exactly analogous to von Neumann-Morgenstern's external stability and strong renegotiation proofness of Farrell and Maskin. If we have something that's externally incentive feasible, it's also going to be an equilibrium in our sense. So the question becomes, when is there going to be a fixed point? And there's going to be a fixed point as long as the constraint set is non-empty for F in the relevant region, because F is the object that we're trying to find. So let's get a handle on that. So let me just spend a few minutes thinking about the properties of my constraint set as a function of F. As I said before, autarky is always internally incentive feasible, so that trivially implies that the constraint set is non-empty when I just put in the autarkic value. So let's define F upper bar as being the largest value of F for which we have a non-empty constraint set. The nature of this, so let's first of all think about impatient agents. So now I've made beta small. Now, what does this inequality here say? This inequality basically says, let's look at an agent who's only alive for 2 periods. He knows he's going to be rich today. He has high income today. He knows he's going to be poor tomorrow. He has low income tomorrow. If this inequality is satisfied, that is, if the discounted marginal utility of low income is smaller than the marginal utility of high income, then this implies that such an agent has no incentive to smooth income, even though he knows he's going to be poor tomorrow. it turns out that if, in this case, that F upper bar is the autarkic utility. That is, if I try to find an incentive feasible allocation for any value of the outside option that is strictly larger than autarkic utility, that set will be empty. So I can't do it. There will be no risk sharing. On the other hand, if we reverse the inequality, even by epsilon, so now there is a marginal incentive to smooth income, then F upper bar is going to be strictly larger than autarkic utility. And this simple consumption allocation you can use to verify this. The reason I'm showing you this consumption allocation is because it highlights an important property of what optimal allocations are going to look like. So what does this optimal allocation do? Well, not surprisingly, since we're thinking about agents being rather impatient, so this means that the rich agent is just indifferent when beta is a bit bigger. He's close to being indifferent between sacrificing a bit of current consumption for future insurance and not sacrificing any consumption. So let's think about the consumption allocation where we sacrifice epsilon of current consumption. Now, you might have thought that the right thing to do is to take this epsilon consumption and then just give it to the poor agents. But the trick here is that we want to be giving this insurance to the poor agents in the way that rewards the high agent for sacrificing consumption. And the way we reward the current rich agent for sacrificing consumption is to increase the value to him of future insurance. And he cares more about insurance in the next period if he was poor than insurance in 2 periods when he's been poor for 2 periods, because that occurs 1 period later. And so that's what this consumption allocation does. Half the agents are rich in any period. Only a quarter of the agents are recently poor. And a quarter of the agents have been poor for 2 periods. So we take this epsilon income from the rich agents and give it all to the quarter of the population who are only recently poor. And that's where this 2 comes from. And this is the most effective way of encouraging the currently rich agents to sacrifice current consumption, because we're skewing the value of insurance to reward the currently rich people. So now let me diagrammatically indicate what's going to be happening here. So V star of F is the value of the exogenous problem. F, recall, is the value of the outside option. So that's on the horizontal axis. On the vertical axis, I'm plotting value. When the exogenous value of the outside option is less than the first best level, that means the value of the outside option is not attractive at all to the rich agents, and so they're willing to fully insure. That's providing agents are sufficiently patient. Beta is greater than beta FB. So for F smaller than FB, we've got first best insurance. Then once the value of the outside option becomes too attractive, now I need to be bribing the rich agents to stay in the agreement effectively. So I need to be doing something in terms of risk insurance to reward the rich agents who are going to be sacrificing. If we're only a little bit greater than the first best F, then I only need to distort a little bit from first best insurance. But as F increases, I need to do more and more distortion from first best insurance, and so V star of F is going to be decreasing. The fixed point is going to be where the T mapping exactly hits the 45-degree line, and so here's my fixed point for a value pi. Clearly, as I vary pi, I'm going to be identifying a different fixed point. If pi is very low, and recall I defined pi of first best, this is the maximal value of social capital consistent with first best insurance. If pi is any lower than pi first best, then we're going to get a fixed point down here. We're always getting first best insurance when we reach an agreement, but with high probability we're an autarky, and so the value of that equilibrium is going to be low. Pi upper bar, this is the maximum value of pi consistent with an equilibrium. And the way I've drawn it here, you'll see that pi upper bar is strictly smaller than 1 because I've drawn this, that at f upper bar, v star of f is strictly greater than f upper bar. The draft of the paper that is on my web page, I would say 99% is fine. The proof that we had for that claim is a enormous thinko. I don't know what we were thinking when we wrote that. It is true that in all of our computational exercises, this is true, but we have not yet been able to prove that for all parameter values we have this situation. I'll come back to this in a few minutes. Excellent. Okay, so summarizing what I've shown you so far, when players are impatient, there's no risk sharing equilibrium. If players are patient, we get risk sharing. The amount of risk sharing depends upon the amount of social capital. Pi upper bar was this critical value of the social capital. When the social capital is less than pi upper bar, the equilibrium is unique. Its ex-ante value is increasing in social capital. And so if we want to be, if we somehow or other could think of social capital as being something a social planner could influence, he would want to hit pi upper bar because f upper bar is the highest value, ex-ante value of the equilibrium. When pi is above pi upper bar, equilibrium allocations will not be unique, but all have the same ex-ante value of f bar. And I will explain that in a few slides. What we do know, so when is pi upper bar strictly smaller than 1? We know that pi upper bar is strictly smaller than 1 when players are patient, but not too patient, okay? What we don't know is what pi upper bar looks like for beta near 1. As I said, our computational exercises still have it being less than 1, but we have not yet been able to prove that. Okay, so now let's think about what do the equilibrium allocations look like in that region where we've actually got our stronger fixed point property. That is when we have external incentive feasibility. So this is a world in which we need to reach an agreement which is not too generous because it'll induce a deviation by the agents, but can do some risk sharing. And as I suggested earlier on with the earlier example, what the allocation needs to do is to discourage secession by the rich agents by allocating insurance payments towards the more recently poor agents. So this is going to give sufficiently high utility to the rich agents who, of course, are sacrificing some current consumption for the poor agents. And because we're biasing the insurance to increase the utility of the current rich agents, this means that if we look at agents who are poor, I can rank the agents who are poor by the number of periods that they've been poor. Have they been poor for only 1 or 2 periods, or have they been poor for a long time? Their consumption is going to be falling. But at some point, their consumption is going to hit a floor, which I've denoted CL. And so what does this mean? This means that the coalitional constraints are binding not only on the rich agents, but also on some of the poor agents. It's going to be binding on the poorest agents, those agents who've been poor for a long time. And it's going to be binding on those agents because they're basically facing the following trade-off. By staying in the agreement, they do receive some insurance. CL is strictly larger than L. With probability 1/2, they'll be rich tomorrow and they're doing great. With probability 1/2, though, they will remain poor. And so they're having very low consumption. By seceding, they sacrifice this current insurance. But because there's still a positive measure set of agents who are poor, by seceding, if they were poor again tomorrow, they're going to receive significantly more insurance. I'll illustrate that in the next slide. So here is a consumption ladder. So basically what these allocations look like is ladders. Here's period T. In period T, if you have high income this period, this is your consumption. If you have low income this period, you have lower consumption. Now let's look at this high income guy. If he gets another high income realization in the next period, he again gets high consumption the next period. That's that green arrow. If he gets a low income shock, his consumption the next period falls to here. People earlier who receive high income always go to the same high consumptions. But you can see that as each agent who was rich at one point receives a further realization of low income, his consumption continues to fall. So this agent here, for example, who has been high income 2 periods ago and then received 2 realizations of low income, has strictly lower consumption than the guy who has been received low income today but high income the previous period. And so that's why deviating coalitions of low agents, since they're restarting these allocations, even if they were poor tomorrow, are going to be better off than sticking in the original agreement, perhaps. Here's a different representation of what these ladders look like. This is going to be useful for something else I want to say in a few minutes. So here, what have I got is I've just got time on the horizontal axis, and now I'm just on the vertical axis putting the number of low income realizations. So I can think of the optimal allocation as being indexed for each high income guy, what his future consumptions look like. So in the first period, the initially rich agents are here. The initially poor agents are here. Then in the next period, either agents get high income shocks or low income shocks. If they're high income shocks, they're here. The guy who in the first period was rich, if he gets a low income shock, he's here. If the guy in the first period receives a high income shock, he's up here. If he receives a low income shock, he falls down here. And so we see these guys, they're going down. The utility to any high income agent from the consumption allocation can be thought of as being the value of these future green dots, because those are always going to be determined by the binding incentive feasibility constraint for the high income guys, and the utilities that he gets from every future realization of low income. And so we've got this decreasing sequence here. And so we want to be thinking about these allocations as a sequence of ladders. Okay, so before I get back to the ladders, I just want to tell you what happens if we're in a real situation where the human capital is above pi up above. So remember, this is the situation in which there is no fixed point when pi is equal to 1. So now what has to be happening? We know there's an equilibrium. So we know there's a consumption allocation where it got a non-empty set of incentive feasible allocations. And so how are we going to do that? Well, we know that F bar is the largest value of F satisfying this inequality, and pi bar is the associated value of social capital. If pi is larger than pi upper bar, I can't make the right-hand side any larger. So the only way I can preserve the non-emptiness of the incentively feasible constraint set is by lowering the term that's multiplying the social capital pi bar. Well, that's W0 of C, the ex-ante value of the allocation. Or in other words, the ex-ante value of the allocation, that is the equilibrium allocation, must be strictly smaller than V star of F bar. And so that's what I mean by utility burning. The agents are deliberately reaching an agreement, understanding that this is not the best possible agreement that they could reach given the exogenous constraint. They don't reach the best possible agreement given the exogenous constraint, because if they did, they know that there will be an incentive for a subsequent coalition to deviate. How should we be thinking about this? Well, the idea is that you basically want, it's analogous to the idea of gift sharing, the exchange of gifts in some of the partnership literature and associated stuff. The idea is that if I'm going to reach an agreement, I need to make sure that the agreement has the property that it's costly to restart. right? So for example, what you could do is postpone the start of risk sharing. So that is, we start in the beginning just by having autarky. If we start in the beginning with autarky, we don't have to worry about coalitional deviations because we're not asking the rich agents to sacrifice any current consumption. Then eventually we ask them to start sacrificing current consumption. Why don't the rich agents at that point deviate? Because V star F bar is so large. Well, the rich agents at this point don't deviate because they realize that if they were to deviate, they would have to start off paying their dues by having many periods of autarky before they could start the risk sharing. Okay. We can also do it by destroying resources. That's what this slide is about. In the interest of time, let me not talk about that. This just summarizes. Let me not talk about that, because I just want to spend a few minutes in remaining to give you a flavor of what's interesting about pi bar. So remember, pi bar was the maximum value of social capital that's consistent with that fixed point of the mapping. So how can we think about the fixed point of that mapping? So now let's go back to my ladder. I talked about, this is a way of thinking about our optimal allocation, but now think about it slightly differently. What have I got here? What's the property of this, the consumption allocation? The consumption allocation you can think of by looking at this picture is as a specification of consumption at every filled in dot, where we're maximizing the ex ante discounted utility of this specification at every dot, and where the resource constraints are all holding vertically. That is, we've got a probability of each of these dots being realized. That's completely a function of, was it high income this period? Was it high income last period and low income this period? High income 2 periods ago and 2 realizations of low income and so on. So it's a half, a quarter, an eighth, a 16th, and so on. And so we just take the resource allocation feasibility constraint vertically. But now let's think about a different problem. Now I want to ask about a stationary ladder. A stationary ladder is where I specify the same consumption at every green dot. I specify the same consumption at every black dot that is reached after one realization of low income. That was reached from a previous green dot. So this one, this one, this one. Ignore this one. So over here, I'm also going to have the same consumption here, here, and here. So that is, in every period, the agents who were rich 2 periods ago and then poor get the same consumption. That's a stationary ladder. So then I could ask the following problem. Look at the utility of an agent who is currently rich. Then he receives low income tomorrow with probability a half, high income with probability a half. Each time the guy receives high income, he was going to receive some utility. Now what I'm going to do is look at the following stationary problem. I'm going to calculate the utility to an agent who is currently rich, and then in each future period is poor with probability 1/2, and I'm just going to ignore the other part. This allows me to think about the utility of an agent, and I can impose now a stationary resource constraint. So this is the resource constraint that I was talking about before, vertically. And I'm going to impose that the poor agents are never so poor that they would want to deviate from the coalition. So this is an artificial stationary problem that focuses on the value to the rich agents of the agreement. Notice that in this problem, I am not imposing incentive feasibility, and I'm just sort of treating this number here as fixed. So this problem allows us to get a handle on pi upper bar, because it turns out that pi upper bar and F upper bar are precisely the critical value of the outside option where the high income incentive constraint is exactly binding, right? So V dagger is the value of this problem. W of H is the value of deviating to the rich agents. And what this theorem basically tells us is that if the value of the outside option is less than F bar, then the rich agents get enough utility from the stationary allocation that they would never want to deviate. Conversely, if F was strictly larger than F bar, that means that the external constraint is very attractive for the poor agents, right? This is where F is entering the constraint. Then we don't generate enough utility to the rich agents in order for them to follow the agreement. Moreover, while that stationary allocation is not an equilibrium allocation, you can show that at F bar, the equilibrium allocation converges to the unique feasible allocation satisfying that equality. Okay, all right, so that last part was a little quick, and I'm not sure how much you were able to get from that, but basically, what's interesting about F bar is that it's exactly the point where all the constraints are just binding in a very precise way. And that's why we think there is some hope to prove that pi bar will always be strictly smaller than 1, but as I say, it's turned out to be a lot more challenging than we anticipated. So here's a conclusion slide that basically says what we said before, but since I've been talking for a long time, let me ask if there are any questions.
I have a question.
Yeah.
Maybe if you don't mind, could you explain the last theorem once again that you had on the slide? It was
this one?
Yes.
Yeah, okay. So I'm just going to go back to the picture because I think it'll be a bit easier. Okay, so first of all, just to emphasize this stationary problem here is basically, I'm not looking at a sequence of consumption allocations for rich agents and poor agents. I'm looking at a single ladder. Okay, so the single ladder is I'm saying, what is I'm going to look at the following sequence: consumption in period 0 for the rich guy, consumption for the guy who was rich yesterday and poor today, and so on down to here. That's going to be a sequence like that. Then I'm going to maximize the utility of the agent in period 0 from this consumption allocation, where I'm imposing resource constraint on that allocation. Now, that I could take that consumption allocation and then now in my original problem use that as a consumption allocation. So that means that in every period, if anybody is rich, they're put onto the beginning of the stationary ladder, and so on. And this is going to be a feasible, and if F is not too large, internally incentive feasible consumption allocation. That is not going to be optimal though, because it doesn't have enough risk sharing in the beginning. What we want to be doing in the optimal allocation is taking some of the consumption from the rich guys and giving it to the current poor people in the early periods. So what that theorem is saying is that even though the stationary consumption allocation is not an equilibrium allocation, when I look at the consumption allocation defined over this ladder, I've got the consumption to the rich guys in the first period, consumption of the rich guys in the second period, and so on. That consumption converges to the stationary consumption of the rich guy. Look at the consumption allocation of somebody who was rich yesterday and poor today. That is going to converge to the stationary consumption for the guy who was only received one low-income shock, and so on.
Okay.
Hi, George.
Okay.
Hi.
I'd like to ask the following slightly technical question. So the model hinges on a continuum of agents, and the fact that, say, with idiosyncratic shock, half of the agents are going to be rich, half poor,
Yep.
and then a quarter was going to be twice, and so on. Now,
Yep.
we know this is kind of not a very mathematically sound model. Is there a way to escape this and do it, say, with a large finite set or something else, or do you actually need the power of this continuum?
I would, okay, so two things. First of all, we do need the continuum here. If we do finite, lots of other questions are going to come up that we didn't want to deal with, because then the problem does not become recursive. So it would be, what makes our analysis work so far is that we've got the same pi ex ante, and then every subsequent potential deviation by the coalition. So we don't even know yet how to handle the case of thinking about pi, which could vary with the measure of the size of the deviating coalition. Because it would be natural to think, for example, that a smaller coalition would find it easier to reach an agreement. So you could have pi being decreasing in the size of the coalition. Or you might think that it goes the other way. I mean, so we would not be able to handle that. But let me clarify the first part of your question. So I think that there is a, one needs to be careful when you deal with a continuum of independent random variables. But because what we're doing here, the way we've constructed this, the issues that you're indirectly referring to don't come up. Because I don't need these income shocks to actually be independent across the agents. Right? I could just put everybody on a circle, for example, and then have all the agents from whose names are between 0 and 1/2, their first income shock is high, and the guys from 1/2 to 1, their first income shock is low, and then just continue drilling down on the unit interval, because we're never using the fact that the shocks are independent across the agents other than to eliminate aggregate uncertainty.
But in your alternative model, then I would know if so I know in advance how many periods I'm going to be rich.
That's
right?
true.
Because there's no randomness.
Oh, no, okay, that's fair. I'd have to think, okay, very good. Yes, yes. That was a little too quick. All right. You have to give me a few more minutes to, it might take me a few minutes, but I'm pretty sure we don't need independence. You're right. We need that each agent can't predict their own future income shocks. Yes, but this is, okay. All right, here you go. It didn't even take 5 minutes. Okay. We're still going to put people on the circle, but in each period, I'm going to spin the wheel so that the origin is randomly determined. All right, so the point is that what the critical feature we're not using is that if I know my income shock, I know which other agents have high income and which other agents have low income.
So you just need, essentially, you only need cross-period independence. For agents,
precisely.
You don't need a location-based. So independence between the age, among the ages is so I think it's rather important that this is clearly stated, because this is kind of
yeah. No.
Again, as I said, it's an not well-founded model otherwise.
That's fair. Yes, you're right. I will write that down, Ron. Thank you.
Thank you.
Sorry, may I have a question?
Of course, please.
So my question is that perhaps a bit off that, can you relate your notion of equilibrium, notions of equilibrium in the cooperative game theory notions? So for example, do you see any connection to recursive core or something like that?
Yes, no, I think the spirit of this is much more cooperative than non-cooperative, because this is all about coalitional deviations, and and I deliberately chose internal stability, internal incentive feasibility, and external to hark back to von Neumann Morgenstern, internal and external stability. So very much, I view this as being very much in that spirit. The one place where, but the timing is something that's sort of different, right? So most of the cooperative stuff takes a sort of static view of this. And for us, it's important that we're thinking about, we have an agreement today, then if a group wants to deviate, there is this penalty that's imposed for one period, and then there's friction with the pi. But I agree completely. I mean, this very much, I think there's, and I think we're seeing this more and more, is that there has been this unfortunate extreme divide between cooperative, non-cooperative. And it'd be nice if it wasn't quite so stark.
Yeah, because, and do you really, so for example, in the notion of few games with uncertainty, Barhabis and Herings in Jet, they have two periods, starting point, 0, and this is ex ante period, and an interim period. And somehow you have something similar. Of course, you have a process. So you have, but what is important, what happens ex ante and what happens interim. So somehow you are very, very, very similar to that, but you have continuing many players, they have only finite many. So of course there are many differences.
Yep. Yeah, and it also shares with like, there's Ray and Vora have a bunch of stuff on far-sighted stability and so on. And the fact that we're looking at this recursive structure of that is also very, very much in that theme. That's right.
Thank you very much.
Yeah, thank you. Unless people have more questions about the slides, I might stop sharing slides so you can all see each other.
George, again, going back to my question, sorry about that. I'm wondering whether in the alternative model that you proposed, you can think of deviations, because now there is dependence among agents. So if I'm rich today and you're poor today, it's very high likely that we will switch roles in the next period. So I might turn to independent agents and have specific deviation from them. Now the deviation is not going to be based on who is rich and who is poor, but I can think of specific agents where I can strike deals with. Because when you turn the wheel, we move together.
Yeah. Okay. So my instinct says no, but that's where mistakes come in. So let me just say, I need to think much harder. I mean, that's a great question. You're exactly right. Great question.
Sorry to push the point.
No. Dog, if I didn't want to get pushed, I'd be still sleeping in bed rather than giving the seminar. Come on. This is why we give seminars, Ron. If you don't want to get pushed.
Yes, I'm just exhibiting standard Middle Eastern politeness.
That's
sorry for everything.
But you're talking to me, Ronnie.
Okay, so are there additional questions to George? Any comments, suggestions? Okay, so thank you all very much. Thank you, George, for this great talk.
Oh, thank you for listening.
And we will meet again in 2 weeks.
Excellent. Thank you. Bye.
George, I have to say it's really nice how such a simple model, you know, some nice questions come out of this. I mean, the model when you presented initially looks very simple, and I said, what's he going to tell us? There's nothing to tell us in such a model. But it's nice. Yeah, thanks. Great.
No, it's been a lot of fun working on this project.
Okay. Have a good day.
Bye. Bye, everyone.
Bye.
All right. Thank you.
Bye.